what we see ourselves as is a new workflow methodology for professional electronic engineers that can help them build products faster, optimize those designs to be more accurate while doing that design, and to give them the opportunity to spend more of their time on the more complicated, more creative parts of their design.
On this episode of Embedded Insiders, Tomide Adesanmi, co-founder and CEO of CircuitMine, dives into his company's Deterministic AI platform that's designed to help circuit engineers quickly take their design process from architecture to schematics. Next, on Dev Talk with Rich and Vin, the two are defining chiplets and whether they're truly a problem-solving solution and how you can implement them into your design. But first, the topic that Rich and Ken are discussing this week is GaN, also known as gallium nitride. They're a bit puzzled as to why the power's transistor technology, although widely known to be efficient, is still slowly being adopted by big semiconductor companies. Stay tuned.
Hello, friends. Welcome to the Embedded Insiders podcast featuring me, Ken Briota, and him, Rich Nass, both of Embedded Computing Design. You can't see us, but I did just point at the camera, so that's a nice sight gag for you out there listening to a podcast. Welcome.
Hello, Ken. How are you?
I'm all right. How about you, Rich?
I'm good. So before we start, we have a little debate that we have to work through here.
Sure.
A taco has a hard shell. A soft taco, what makes it a taco if it's not a hard shell?
All right. Welcome to Sandwich Talk, folks, but we are here for this. A taco can be hard or soft shelled. They sell soft shell tacos. I think that the hard shell taco is inferior almost all the time, with the notable exception of homemade. Homemade is good because they have a little bit of give on them. When you buy the store-bought ones, they just shatter immediately. They're impossible to eat. So
and the difference between a soft taco and a burrito?
Is mainly the filling, I think, and the size. Soft taco is significantly smaller, but is substantively not different. And I will say, I think that most folks would agree that the burrito is in fact American food and not Mexican food. So that's probably also a significant difference.
Okay, now I want to know how you're going to segue from that to gallium nitride components.
Easy. Have you ever eaten at Taco Bell? You've probably.
There goes one of our sponsors. Thanks a lot.
Oh, no. I think Taco Bell would have a sense of humor about it.
Okay, so let's segue to power components, which is a little more in our space than tacos. Gallium nitride. I recently spoke with an old friend, Rupert Baines, who's he's been in the RISC-V space for a while, and I've known him probably for better than 20 years. But he is in the process of becoming the CEO of a company called QPT. He doesn't actually start, I don't think, until April 1st, but he's very well entrenched. And when we were talking the other day, he was talking like he was the CEO and he knows the stuff. But what they're doing to differentiate themselves, they're a startup. It's a single product company right now, and they are doing motor controllers using GaN. And that's something that hasn't been done before, as far as I know, because of the power space, power levels that we're talking about. It had traditionally been something that was done with silicon, and then it went to silicon carbide because the power levels were so high. And traditionally, GaN breaks up if you get to those power levels when you're talking about kilowatts. And they have come up with this technology using, and to be clear, they're using other people's GaN, and they're taking it and packaging it into an IC for a motor controller. But the one of the hard parts is the software that goes with it. Doing the models for motor control is really hard. So I'll stop there because I've talked a lot. But it's pretty cool stuff. And unfortunately, I'm not going to APEC this year. So I'm trying to reach out to a lot of these guys ahead of time to see what's the latest and greatest. And this was one of them.
Yeah, it's funny because the gallium nitrate silicon carbide thing was a big topic of conversation when I met with Navitas at CES. Actually, we were talking mostly about transformers, converters, that kind of thing, of course. But they were really excited about GaN and have been putting it in consumer products for a long time. They've partnered with um they sort of started in the like charger and charging block world and then have moved up, and now they're in full transformers. There's some really cool they had a whole like showcase room where they were showing off a bunch of the different in the field things, lots of interesting server applications for that, because of course you've got all this heat, and the heat and stuff can impact traditional silicon. And then with enough heat and a big enough server space, you're actually impacting the GaN uh, level too, so that they're also making silicon carbide versions for the higher power level and potentially higher heat stuff too, which is pretty cool. I thought it was really interesting.
So you know what my problem there is? No one has convinced Apple to go to GaN.
That sounds
And
like an Apple problem, and I'm shocked. Oh, are we switching to talking bad about Apple? Because I'm okay for that.
I'm not talking bad about them, but they just won't make this move. And I have a bunch of these GaN chargers, and I stick my iPhone on it, and it does not charge in 19 minutes like the GaN guys say it will, because they throttle it back and
Yep.
they won't allow you to charge at these higher power levels. Hopefully that there's something in the works to fix that, because once you start with an iPhone, you're sort of stuck with it, and it's not that I don't like it, but I am stuck with it because I'm on like my 6th or 7th iPhone. My family's on it. All my coworkers are on it. So we have to stay with the iPhone. But why not put the ability to charge with a GaN charger, so I can charge this thing to full power to 98% in 19 minutes?
Yeah, I mean, I don't know. I've never really understood, like, I get that there are some arguments for why Apple is slower to adopt certain things, and that just, joking aside, I get it. But for in this case, it doesn't make a lot of sense to me. They want to all of these cell phone companies want to talk about their speed of charging. This seems like the lowest barrier to entry for that right now. And all of the other manufacturers, I think all the other major ones anyway, are GaN friendly.
Yep.
So it seems like a weird thing to not be doing yet. And I mean, it's a supply chain issue too, you'd think, because you don't have to import all of the manufacturing. That's changing a little bit now with the the builds that are happening, but there's already uh supply chain and manufacturing in the US for GaN, and very little for silicon, although hopefully that's changing.
And some of the big guys are scooping up some of the GaN guys, like GaN Systems is now part of Infineon. Renesas just made an acquisition. So it's very clear that this is the future, the very near future.
Yeah. You think the industrial folks are going to take to silicon carbide and doing stuff that way, the way that it seems like the consumer facing groups are all doing GaN?
They will, but they're a little slower to adopt for some pretty good reasons. It has to work every time, all the time. Can't have any downtime, so they're much more risk averse. And also, it works, so why should I change it? Is a lot of the mentality.
Yeah, until it doesn't, I guess, is the counter
Right.
argument.
Yeah, exactly. But
Yeah.
in most cases, that's when the upgrade happens, when it doesn't work anymore.
Yeah. I suppose I'm not a sales guy, but I suppose that there's a lot of talk about redundancies and like, well, we can layer it and you'll have your thing that you're used to as a backup, and you'll see that you never end up using the backup, and blah, that kind of discussion is probably the early phases discussions. Yeah.
Agreed. But this is cool stuff, and this is sort of a preview of APEC, and we'll probably do another APEC preview because it isn't for a few weeks out. So as I get more into it, I will educate the audience, hopefully.
Absolutely. And while we've got the folks out there listening, this is our early and important reminder that Embedded Computing World is coming up. And if you're going to be there, let us know.
Embedded World.
Embedded World. Yes, that's what I said, isn't it? No. Embedded World is coming up. we'll be there doing a bunch of stuff. And if you're going to be there, folks out there listening, you should reach out. Let us know so we can talk to you about some stories and what you're going to be doing at the show.
Now, here's Tomide Adesanmi, co-founder and CEO of CircuitMind, discussing his company's solution for generating circuit designs with architecture-driven deterministic AI.
I'm Tomide. I'm the co-founder and CEO of CircuitMind. Before CircuitMind, I was an electronic systems engineer. So I used to build helmet-mounted display systems and heads-up display systems for jet fighter pilots at BAE Systems. I got tired of reading data sheets, so I started CircuitMind about 5 years ago now to tackle some of the problems with getting to market faster, developing better products, and also reducing the number of respins and errors that we run into as electronic engineers building a new product, as well as supply chain issues. I met my co-founder, Basilio, who's got 2 masters and a PhD in algorithm design. And his background in algorithms and my background in electronics was a very good combination to start this company.
In your opinion and with your experience in circuit design, what are some of the problems and or challenges surrounding the development of electronics or circuits today?
Yeah, there are a few. I guess the first one is there's just a lot of manual and tedious tasks that lead to the opportunity to make mistakes. And mistakes are in the circuit design process are very they involve a huge penalty. That is months of delay, because if you make a mistake and you have to do an unplanned respin, it takes you kind of months. The second one is that we're not given the opportunity with the tools we have today to do the best possible design that we can. And what does that mean? That just means that there's so many components out there. You need to delve into data sheets to figure out if you have the right component. There's so much data around whether a component is supposed to be useful for you, in lots of in many pages of data sheets, but also in supply chain information, end of life information, aggregator information that's brought together by aggregators like Octopart and Z2 Data. And so when you're doing component research, you are trying to find the best component or best combination of components for your needs from a huge mountain of data across different information sources. This is very difficult to do, and it's very difficult to do that and balance and optimize your design for cost, size, power, supply chain, performance, and so on. So this is the second big problem that I see. And then the third big problem is simply that, it's given all of this stuff, given the errors you make, given the kind of component research issues, it takes you a long time to go through the whole process of, first doing your requirements, selecting your components, etc. And during the design process, you end up changing requirements, or the customer ends up changing requirements, and you have to go back and do some of these again manually. So all of these challenges are kind of make it very difficult to be agile in the electronics design process.
So I know you've developed a deterministic AI that can generate circuit designs requirements in 60 seconds. So before we get into the details of that process, can you, in your opinion, tell us how you define deterministic AI and what industries benefit the most from this technology?
Artificial intelligence these days is a buzz term.
Yeah.
It's incredibly popular, but it's also quite misunderstood. The way we think about it is that what we care about for professional electronics engineers is building algorithmic approaches that help them with the circuit design while also being accurate. Using some of the techniques like machine learning and large language models are simply not good enough. We've tested them, they are just not that great when it comes to creating a companion that's accurate and gives good results for an electronic engineer. So our approach is actually a bit different. Um, Basically, what we do is we've built mathematical algorithms that are encoded with circuit design principles and that operate on a digital twin of electronic components information. And that digital twin, all that means is all the information you'd normally read in data sheets about a component, as well as the supply chain information, etc. We've digitized them and created a machine readable model of that component. And so these algorithms can go and read those models and perform mathematical operations on them, looking at all those components against each other to find the ones that meet your requirements, can work well together, and give you a good component selection and an initial schematic without errors.
So, can you give us some information about how the AI handles user input and feedback during the design process? And is there any room for manual intervention or tweaking by the engineers, during or after the automated design?
Absolutely. So the idea of this automation is to be a companion to an engineer. It's not supposed to do your design for you, and you kind of leave it alone. That's why it's a tool for professional engineers, electronic engineers. So the idea is it does parts of your design for you, and you do the rest of the design. It helps you do more routine tasks while you do the more creative parts of your design process. So there is room for so basically the way you input your requirements is you create your architecture block diagram. So today you're probably creating a block diagram in Visio or PowerPoint or on a piece of paper. We allow you to capture that within our platform in a sort of with a sort of drag and drop interface. You can also specify lower level requirements on each of these blocks about what you care about. So for instance, for an accelerometer, you might want to specify the resolution or the axis, or for a microcontroller, might want to specify the core architecture, or you might even want to specify the specific part number you want to use because you might have already made that choice. So you can do that within our platform, specify, create a block diagram, specify requirements on each of those blocks. And then you can specify trade-offs with a slider, with some sliders like, size, cost, power, and so on. And just click a button and it generates some parts of your design. What we're trying to introduce is this idea of architecture-driven electronic engineering, where you capture your full requirements with a block diagram. Parts of those blocks will be fulfilled for you with these algorithms, and some of them you might have to do for yourself, because some of them might be just more creative parts of your design, or very complex analog and so on and so forth. And then of course it's your job um, to be the architect, change the architecture and explore a different design option. It's also your job to modify the design to meet your, a certain reliability standard, or some certain last mile design choices that you might want to make. And then it's also your job to do the more complex and creative parts of your design, like the more complex analog bits. So it is a companion. It is a assistant to a professional engineer.
So I know you spoke a little bit about integration, getting more into integration and compatibility. How easily can the solution integrate with like existing design tools or workflows, or compatibility with common industry standards or hardware platforms?
Yeah, so the output is a schematic, and this schematic is designed, it's there are a lot of outputs actually. You can get schematics, bill of materials, can get a lot of documentation, power analysis. It is what you make of it. That's that new methodology, architecture driven electronic engineering. And so once you do that, you need to be able to kind of, integrate with your design flow. So we integrate we integrate very easily with your ECAD tool, whether that is Altium or Cadence OrCAD, div trace, pads, and so on. we're doing more, depending on if a client comes to us and needs a new integration that we don't, new export that we don't have, we can work, we can work on it. It doesn't usually take a lot of time. It's not a limiting factor at all. So we export to the major CAD formats that people use.
For the future, what are your plans for, future developments or improvements of the solution? Or are there any specific challenges or areas you're looking to tackle next as far as the development of your technology?
Yeah, so there are there's a very long roadmap. We're hyper focused on the front end of your design and development process, but there's a lot of integrations we can do. There's a lot of documentation we can help you generate. One of the big things we've done recently is we're helping people generate stress and derating analysis, helping them, we're working on helping them generate their, interface control documents, failure modes and effects analysis templates. So there's all this sort of stuff that can come out of the fact that you can automatically generate, the initial versions of your selected components and schematics. Obviously, we can also take in your own preferred parts and so on. So in the future, we're doing more. We want to help you generate more, like, some parts of your test case documents or and other sort of documentation like that. But there's also things in the pipeline like expanding the component categories that we can help you automatically generate, like more complex analog things. But that would all be determined by how we work close with our clientele. So yeah, there's a lot, and of course there's the kind of going into layout is another thing, but that's not something that we're focused on at the moment because there's so much to do in generating and optimizing component selection, architecture, component selection, and schematic design, as well as schematic verification and review. What we see ourselves as is a workflow methodology, a new workflow methodology for professional electronic engineers that can help them to build products faster, to help them optimize those designs, to be more accurate while doing that design, and to give them the opportunity to spend more of their time on the more complicated, more creative parts of their design. So it's like working hand in hand with their current manual ECAD process, using this sort of automation workflow called architecture-driven electronic engineering.
Now, here's Rich and Vin discussing chiplets, what they are, how they work, and how you can implement them into your design.
Welcome to Dev Talk with Rich and Vin. I'm Rich Nass, Executive Vice President of Open Systems Media, and I lead the embedded computing design team. And that guy on the other microphone is Vin D'Agostino, who is the guy who answers my questions. Whether he knows the answer or not, he makes up answers, and I don't know the difference. So we're going to assume that they're true. How you doing, Vin?
Good. How are you, Rich?
I'm doing just fine. Thank you very much. So topic du jour, I need a little education here.
Okay.
Everybody's talking about chiplets. What's a chiplet?
Everybody's talking about chiplets. So chiplets are basically ICs that have been put together with some building blocks at a higher level than they're doing now. I mean, if you go to any semiconductor company, let's say it's an MCU company, they have A to Ds, they have D to As, they have timers, they have UARTs, and they have some logic and or compute engine and memory. They aren't redesigning every one of those for every chip, right? They already have a library and they have their favorite 12-bit A to D or their favorite three-phase timer for doing motor control. But it's very much in their library, and the interface between that and the rest of the chip is pretty defined for that particular family of design. So if you had, let's say, 3 different families of MCUs, the interface on a UART might change depending on which family you're using. The chiplet, I hate to even say this because then the software guys will say we won, but it's almost like having an object that is hardware, right? And it also allows you to potentially create lower volume and more flexible designs. And it is fun and it's new, but it's kind of not really that new too.
Is it similar to a multi-chip module?
Well, it's funny you should bring that up, because that was the kind of example that I was going to use. If you look at building any kind of product, you've got technology, you've got process, and you've got manufacturing. And any one of those three innovations can bring the product forward. And those three things can sort of play off each other to continue to bring forward. The example that I would use back in the 90s-ish, let's say early 90s. Some of our listeners are actually old enough to remember the 90s. When you wanted to make a modem, you had to buy 3 chips. They were 3-chip modems, and that was it. And they were not difficult to design with, but certainly not easy to design with. And let's also go back to the fact that most people were not designing PC boards in a computer at that time, right? It was
Well, what were the 3 chips?
So there was the analog front end. God, I knew you were going to ask me that. I should have looked up the 3 chips. There's the line interface, which includes the analog front end. There was the
Our listeners can chime in with
the basic computing part, and then there was basically the glue logic. But yeah, anyone who worked in that, I actually joined working with modems when the quote unquote single chip modem came out. Okay. And at the time, I had just started working for XR, and they had a 2-chip modem set because they had a mixed mode process, and they were able to integrate some of the analog with some of the digital stuff. That was one of the problems, is that the analog stuff had a certain voltage, right? Because your phone line and all that, the digital part was a different voltage. The chip was going to be too expensive, because if you made the feature size of everything big enough to deal with the high voltages. And so we had a 2-chip modem, and we thought we were really cool. And we actually only made the one of the 2 chips, and then you combined it with the compute engine of somebody else's chip. Rockwell, who actually made ICs back then, they made 6502 microprocessors, which is really, if you think back on that, they came up with what they called a single chip modem. It was one package you put on the board. Don't forget, people were laying boards out on acetate with Mylar tape and X-Acto blades. So, every trace you put down cost you a fair amount of time and money. It's not like now where you can just click and drag, right? Everyone was shocked at how they could come out with a single chip modem. They were Rockwell. They weren't a semiconductor company. They had a semiconductor division to make some specialty parts that nobody wanted to make for them for their aerospace business. And then somebody popped the top, and they realized that all they did was take the 3 chips and make a multi-chip module. They were at the pinnacle of IC manufacturing. And so instead of innovating in technology or in process, they innovated in manufacturing and made a single chip modem. And that is a big deal. This is,
and you're saying that that's the same as the chiplet of today?
I was going to say this is the on IC monolithic version of that philosophy. In this case, it was an innovation in process, right? How are we going to make the process innovation to be able to have people put these chiplets together and make a system on the chip, right? And you couple that with some of the manufacturing advancements that have been made, where, there was a time where if you were a semiconductor company and you wanted to make a test chip, you had to buy a whole wafer. And now with mixed shuttles, you can actually have your die on a wafer with other people's die, and it runs through, and it's not costing you as much to run your test chips. So that is now an innovation in manufacturing. And of course, the innovation in technology would be things like feature size, circuit design, that kind of stuff, right? So you take those 3 things and you put them together, and you innovate in one, which makes the product dramatically different for the marketplace. And that also allows you to capitalize on or force changes in other pieces of the puzzle to make things move further or move forward even further.
So let me ask you a question.
Sure.
What's a chiplet?
Chiplets are the little pieces, the little modules that get put together. It's the chip version of an applet, right? It's not a full application, but it's a small part of an application that does one thing really well. This is a small silicon design that does one thing really well, has a defined interface that lets you snap together other chiplets and put a system together on the chip.
Okay, that actually makes sense.
And I would say that it is a combination of circuit and layout, because what's one of the other things, right? You can have circuit blocks and you put them together into a schematic, but now you need to lay them out on the chip, right? The chiplet has the layout with it. And so as you snap these things together electrically, you're also snapping them together physically to some extent, right? With anything, there's going to be limitations, but it lets you kind of say, I want, 2 from column A and 1 from column B, and put this together and make me a chip.
So that means it's not being done at the die level.
I mean, ultimately, everything is done at the die level, right? I mean, communication has a media, even though you have a 7-layer model, it still has to go out the wires. So at some point, it is done at the die level, but the concept and design part is not being done at the chip level. It's being realized at the chip level once everything is synthesized together.
And how do I test this chiplet?
Well, there are 2 layers of design minimum for every one of these systems. There is the verification that each section works, and there's the verification that the overall system meets the design spec, which is kind of like a black box design. You have designed and spec'd some excitation and some result, and you run through that. Now, you have to limit it, right? If you say, hey, I have X amount of memory, it's going to take me forever to diddle every bit every way. And so, there are rules and criteria for figuring out a statistically significant subset of tests that makes you believe that the chip works, right? But you also have some specific function that you like, hey, if it was a thermostat chip that you built with chiplets, that by varying the temperature, you expect the output to turn on and off, right? That's a very simplistic viewpoint, but that's your ultimate black box design test. I go above the set point and it turns off. I go below the set point and it turns the heat on, right? There's obviously display and all other kinds of things, but that's the...
Is this something for the long term, or is this a short-term fix that'll be displaced by something else? And that's a crystal ball question.
I think it'll always be a piece of the long term, but I think it's going to lead us to something that that pushes the design even closer to the system designer and not the chip designer. So I think this is a step in a process. It might remain a step in the process for a long time. But I think this isn't the holy grail, like this is where we're going to stay forever, right? It's not quite as bad as when they started talking about streaming and it was really a bunch of guys running around at the home office putting tapes and VCRs that were targeted to your house, right? That was a short-term solution to streaming. But it is definitely going to be part of the process for a long time, but it won't be the long-term solution, I don't think.
Okay, sounds good. I'm going to dive into it a little further. Maybe I'll have something to come back on this subject.
Maybe some of our listeners or readers can give us some examples of things that they've done or they're thinking about doing, and we can maybe even put together a little roundtable with some manufacturers who are playing with chiplets and ask some deeper questions.
That would be pretty cool. Thank you, Vin. That was Vin D'Agostino. I'm Rich Nass, and this was Dev Talk with Rich and Vin.
Thanks for listening to this edition of Embedded Insiders. For more daily news, videos, and podcasts, visit our website at embeddedcomputing.com.